Okay, we are on page 5 back in your packets today, and we're gonna combine what we looked at the last couple of days with what we saw at the very start of this unit, okay? So at the very start of our unit, we did a little refresher on writing polynomial functions given the zeros, which we'd actually done in our first unit, except we called them x-intercepts instead of zeros. And we had talked about the fundamental theorem of algebra, which is this idea that however many zeros I have should match the degree of my polynomial. And as we first introduced this idea, we talked about how sometimes that number of x-intercepts didn't match the degree, and that meant that we had imaginary zeros, which we just spent the last couple of days working on. So today we're going to combine these two ideas: imaginary zeros, what they look like when I write a function, and that fundamental theorem of algebra idea that my degree should match my total number of zeros, okay, both real and imaginary. So on page 5 today, we're going to write some functions based on the zeros that were given. Anytime we're writing polynomial functions based on given information, I want to just use the information that I'm provided. So don't add in exponents if I don't see something listed multiple times. If it says in your directions, assume your lead coefficient is 1, and you don't have a reason to think that it would be -1 or 15 or something like that, just leave it as 1. So that's what we're saying here. Assume least degree possible based on the given zeros and a leading coefficient of 1. And then here's sort of the extra part that we'll get because of our imaginary zeros. Our final function should be in all real numbers. Okay, we don't write polynomials typically with imaginary numbers. So my function, my final answer, should have only real constants and coefficients. Okay, and then we'll talk about that in just a second. So for our first example, this looks like something I could have given you the other day or in our last unit. So I want to write a function that has these zeros. So this would look like x minus 2 times x minus 3 times x plus 1. What's the degree here? 3. The degree for this function would be 3. Now for our second example, we're going to see something a little bit different. Okay, we've got some imaginary zeros listed here. So as I go to write my function, I would have, if my 0 is at 0, we could write x minus 0 or x plus 0 if we wanted to, but that would just simplify to x. So I would get x here. Since I've got 0 listed twice, I have x squared. And then I've got 1i, so I would write that as x minus 1i. And then I've got negative I, which would be x plus 1i. So I treated these imaginary zeros the same way I treated my real zeros. Okay. But now I've got one more step to do. Because I want my function to have only real constants and coefficients, I've got to multiply these guys together so that I don't see those imaginary numbers. Okay, so I'm just going to distribute. We've done that before. I'm just distributing these two imaginary factors together. So I get x squared plus 1ix minus 1ix minus 1i squared. Now, the other day, I mentioned how your imaginary zeros are always going to come in pairs. They're always going to come in opposite sign pairs. So what we would call like complex conjugates. So this I could think of as a complex number 0 plus 1i, and this would be the complex number 0 minus 1i. We could see other real parts here, but let's just focus on the I parts. My imaginary parts are always going to have opposite signs. If I had, and we'll see here with our fourth example, a true complex root, not something that's purely imaginary, then I would also have what's called complex conjugate. So if I've got 1 minus 2i, I'm also going to get 1 plus 2i. There's a reason why my imaginary numbers are always going to come in these pairs, these opposite sign pairs. And you looked at that a little bit yesterday when you were simplifying square roots. We know when we simplify a root, it's always going to be plus or minus when I take a square root. So if I took the square root of -4, it would be plus or minus 2i as my solution. And so that's what we're seeing here. When we multiply these back together to make our polynomial function, what happens is that the ix terms are going to end up sort of canceling out, right? When I go to simplify, when I combine my like terms, 1ix minus 1ix means I've got no ix term left. That should happen every time, okay? Because I'll always be multiplying these sort of opposite sign imaginary factors together. So I'm always going to have a positive, whatever the ix term is, and a negative, whatever the ix term is. And then at the end, I should have an I squared term. Now, like for this one, it's minus 1i squared. It might be minus 4i squared or minus 100i squared. But I should get an I squared term. What do we know about I squared? It's equal to -1. Since I squared is equal to -1, that means here, what I actually have is -1 times -1, which is +1, which is a real number, right? That's not imaginary. So what I actually get out of here would be x squared plus 1. I'm going to just plop down my x squared term that we had from before. And that is my function written in all real numbers. Anytime I give a function, I want to give it in real numbers. So that's my function that has all of these zeros, but written in real numbers. Now, this factor should look vaguely familiar. We saw a couple problems like this in our last unit when we talked about factoring with difference of squares. And we said, hey, 2 terms, even degree. Oh, it's not subtraction. I guess I can't factor it with difference of squares. What we meant was we can't factor it with real numbers using difference of squares. But it is actually sort of really similar to that difference of squares pattern, just with imaginary numbers for those factors. That sort of similarity makes sense? Okay. Let's take a look at another one. Same idea. So for our third example here, we've got 3, -2, and 4i. Now remember, our imaginary zeros always come in pairs. So if I have positive 4i, what do I also have to have? -4i. They're always going to come in those opposite sign pairs, always. So even if it's not listed, I know I have it. That's the only adjustment that we're going to make to our list of zeros. If they only gave me one imaginary zero, I know I've got another one. So I'm going to go ahead and start my function here. So this would be x minus 3 times x plus 2 times x minus 4i times x plus 4i. And then I want my final function to have only real numbers. So I've got to multiply my factors with imaginary numbers together. So just like we did before. So this would be x squared plus 4ix minus 4ix minus 16i squared. Now, just like in our last problem, those ix terms were same coefficient but opposite sign. That means when I combine like terms, I didn't have it anymore, right? It was just 0. Same thing here. And then again, just like before, we have this I squared term. We know that I squared is -1. So what I have here is -16 times -1. So I could simplify that to positive 16. And this factor just becomes x squared plus 16. So there's my function. What's the degree for this function? Four. 1, 2, 3, 4. How about this guy? What's the degree for our second example here? 2, 4. Okay, now let's look at this one. I'm going to start the same way. X minus 8, X plus 3, X minus 1 minus 2i, and then X minus 1 plus 2i. Since the 1 is positive in both these cases, that's why I'm seeing subtraction here. Now these guys have imaginary numbers in them, so I've got to multiply them back together. Since there's 3 terms, my distribution is going to be a little bit longer this time. That's okay. So here I get x squared minus 1x plus 2ix minus 1x plus 1 minus 2i minus 2ix. That would be plus 2i, and then minus 4i squared. Now I want to combine like terms and simplify. This is my only x squared term. Then I've got minus 1x minus 1x, so that would be minus 2x. So I've combined those. Plus 2ix minus 2ix means those are gone. Minus 2i plus 2i, those are also gone. My only other term with an I is minus 4i squared. We know that I squared equals negative 1. So this is actually negative 4 times negative 1, which would be positive 4. So then finally I've got 1 plus 4, that's 5. So these two multiplied together give me this, and then I've got x minus 8 times x plus 3. What's my degree for this guy? 4. Really quickly, I want to take a look at this last factor we have here. In our last unit, if I gave you this and asked you to factor it, you would look for factors of 5 that add to negative 2. Well, your only factors of 5 are 1 and 5 or negative 1 and negative 5. Do either of those add to negative 2? No. So in our last unit, we would have said this is not factorable. What we actually meant was that I can't factor it with only real numbers. There are factors that would multiply to give me this thing, but I have to use complex numbers here, right? We had complex roots that gave me these factors. Okay, so just a little vocabulary adjustment to some of the things that we saw in our last unit for stuff that we talked about not being able to factor. There technically is a way to factor it, but I have to leave the real numbers to be able to get those factors. Questions for me? Okay, with the rest of our class time today, I would like you to work on the problems at the bottom of page 5. So notice you have exactly the same directions. Give me only real constants and coefficients in your final function. Don't forget to give me the degree, okay? And remember that we will always have imaginary or complex solutions in pairs, okay? So if you have, for example here, if you have 6i, what else do you have? Negative 6i, yep. So be careful with your list. Make sure if you've got one that you have the other as well.